Okay. Hear me in the back? Say something. Can you hear me in the back? No, you cannot. Okay. Well, it says that there is battery. Let's try another one. Hello? No? Okay, thanks. It's okay now? Okay. So, before I start, two things. One is, I think registration is all done. I know that there were 2 people that were left over, and as of this morning, they should be okay. Any complaints, issues, mistakes? No, okay. So some of you need signatures for me, so please come at the end of the lecture and I'll sign. 2, there were a couple of typos in the first homework. I think they're all fixed, and it should be online, the version. So please take a look if you didn't know about it. Questions? No questions. Okay, so let me start by sort of talking a little bit about where we are. So we started talking about learning algorithm just to get an idea of what this class is about. We talked about stochastic and gradient descent with least mean square. We talked about decision trees. I gave some hints about rules. We didn't really talk about learning rules. And now we know enough that we can start asking the question of how are we doing? We're running learning algorithms, but is it doing what we want it to do? And in fact, how do we even ask the question? So today I'm going to start talking a little bit about it, and I'm going to try to quantify it in the simplest way possible. So we're going to look at how many mistakes are we making, or how many mistakes will our learning algorithm make. Not the only way to measure performance, but one of the ways to measure performance, perhaps the simplest, as we'll see. This is going to lead us to another family of learning algorithms. The most important one, perhaps the most important learning algorithm that you learn in the class, is Perceptron, that hopefully will start at the end today. And we'll see a lot of variations of it. Some variations that will address the question of how do we want to deal better with large and sparse feature spaces. some other variations that deal better with overfitting. And we'll also see that we can close the loop and go back to gradient descent that we started with, because this is a very important idea. We'll also look at other representation of perceptron, what's called dual representation, that will lead us to ideas, the ideas of kernels that have to do with more expressive features. So that's kind of an outline of what we're going to do in the next couple of weeks. Today I want to take a more general perspective. Because the weather is changing, we can relax a little bit. We can talk in general about learning protocols, quantifying performance, and we'll see that this actually is going to motivate a lot of the things, a lot of the ideas that we're going to see next. Okay, so I want to start with quantifying performance. Basically, we want to be able to say something rigorous about what we're doing, about the performance on the learning algorithm, and today we're going to concentrate on one way to quantify performance, which is the number of examples one needs to see before we can say that we are okay. That the learned hypothesis that we produce is good. So let's start with this problem. I will not comment about the relation between this and something that you've seen in the problem set. It's a little bit related. At least it will drive your thinking, hopefully. But this is the question we're asking today. So we are dealing with the class of conjunctions over 100 variables, say. And there is a hidden monotone conjunction. So just for simplicity, we'll just talk about monotone functions. So none of the variables is negated. That's my assumption. And I want to ask the question, how many examples does one need to see in order to learn this hidden conjunction? And of course, how it's going to happen. Ideas. 2 to the power of 5. One suggestion. Other suggestions? 2 to the power 100. That's a lot. Hopefully we don't need that many. But it's an option. But before we continue, actually I want to say, you could have complained. You could have said, you know, your problem is ill-defined. And it is ill-defined. So let's think a little bit outside the box. So I didn't even define what is the learning protocol. And you could complain and say, you know, there are many protocols that you could invent, and within each one of the protocols you can ask this question. So let's be a little bit more specific. Here is one, here are several options. Here is learning protocol 1. In this protocol, the learner is going to be the one that proposes instances as queries to the teacher. Right? So I'm assuming all the time that the interface is via examples, right? But there could be several ways in which these examples are generated. And the first one here, the learner is active. He says, here's an example, tell me, is it positive or negative? This is protocol 1. Protocol 2, the teacher that knows the hidden function proposes examples, and the goal of the teacher is to help the students, and they would propose examples that maximizes the benefit of the learner or minimizes the number of examples that the learner needs to see. And the third protocol will be probably the one you had in mind, because we kind of hinted on that earlier. Random source, nature, provides you examples. So you just wander around and you see examples. And nature also provides labels to these examples according to the hidden function. So these are 3 different protocols. Let's think about the first. Yeah? The second one, the teacher provides training examples, and we are under the assumption that the teacher chooses examples in the best possible way. So they really want you to learn quickly, and they will choose good examples. In the third one, there is some probability distribution. You just wander around the world and you see examples. They come from some distribution. Some of them may not contribute to learning so much. Okay? So first protocol. What would you do with the first protocol? Yeah?
So you just start with...
Very good. So your first idea when you work with protocol 1 is to say, let's assume that all the variables are there. So it's a full conjunction. You can think about it this way. And then you choose examples to validate the presence of each one of the variables, right? So you're going to, and this really hinges on the assumption that it's a monotone conjunction. So we are going to ask, is X100 in our conjunction? The way we're going to ask it is by turning off X100, and we're going to ask, what's the label? In this case, I'm going to tell you the label of this example is 0. It's a negative example. Your conclusion is we need X100, right? Because it's a conjunction. Agreed? And then you're going to ask this on X99. It's a positive example, so we don't need it, and so on. So this straightforward algorithm is going to require 100 examples. Everyone agrees on that. Now, here is a question. What happens in this case if I drop the assumption that the conjunctions are monotone? Okay, think a little bit. In fact, the same thing exactly is not going to work, yeah? This is a step in the right direction to double the number of variables, basically to have x1 and not x1, x2 and not x2, and so on as a batch of variables. Will this algorithm work as is? Yeah?
They would always return false.
This is in general a good trick, and we're going to see that sometimes it helps. In this context, at least I don't see how to make it work in a simple way.
Can't you do both tests like one?
Ask it again.
Like, do it for each of them, do 2 tests?
Okay, but the game we're playing here is the interface is only via example. So I have to generate an example, ask for the label, and from the label derive a conclusion as to the presence or absence of this variable from the conjunction, or literal. Let's call it literal in the general case, because I don't know if it's positive or negative. So the bottom line is, I think that it's not as simple now. But you may come up with other ideas. So think about it. It's not so simple. My solution to it is to say something like this. If you know of one positive example, if somehow nature or the teacher or you guess, you're lucky, and you find a positive example, from that point, you're in luck. You can actually run the previous algorithm with slight modification. If you don't know of a positive example until you reach a positive example, actually I think it's hard. But anyhow, this is something for you to think about. I want to move on, so it's a challenge. Think a little bit about it. Second protocol. This is a protocol where the teacher that knows F is going to provide the examples. So imagine that you are the teacher, and you want to teach someone as quickly as possible which conjunction is the hidden conjunction. What would you do? Yes. Yeah?
I would divide all of the
So specifically in this case, what do you mean by categories? I don't have any. There's no difference between. The teacher, because he knows classes, but the teacher knows exactly. And the teacher is, so the teacher knows which variables are important and which are not important. That's the game we're playing. And he just wants to give you examples, the minimal number of examples, so that you will also figure it out. Yeah?
So you can give an example by setting one.
Right. So this is probably the most efficient way we can do it. Basically, we're giving you one positive example, and we're giving you the smallest possible positive example, or the lightest positive example. So in this case, I'm going to give this example. I'm going to put on only on 2, 3, 4, 5, and 100, because I know that these are in the conjunction. And basically, what I'm saying here is I'm giving you, because I'm telling you this is a positive example, I gave you a superset of the important variables. From now on, I can run with the previous algorithm. And essentially, I'm going to turn off each variable separately. Right? So now I'm telling you, OK, if I turn off x2, you see from 1 to 0, and the example now becomes negative, you know that x2 is essential, and so on. So we're going to do this how many times? Overall 6 times, right? So in 6 examples, the first one, and then turning off each one of the 5 variables, you learn it. So you see, good teachers sometimes can save time, right? This is a proof that it's better than the previous protocol. So maybe machine learning can tell you something about learning. I don't know. Let's move to the third protocol. So, OK, so by the way, I do want to comment that modeling teaching in a formal way is actually tricky. So there is some literature on that, and it's still a very interesting problem to try to derive learning algorithms that are cooperative, right? So someone really wants to teach someone else something in the most efficient way, but the bandwidth is restricted somehow. You can't just tell them that's the conjunction, because that's not going to be interesting. And you know, it's often in real life this is not going to work, right? You have to figure out ways to teach something in a way that people can actually do something with it later. But if we try to formalize this, there's a lot of tricky issues there, because I need to formalize it in such a way that just giving you the conjunction is impossible in the formal way I define it. Nevertheless, it's interesting. So again, this could be, in fact, an interesting project if people care about it. There is literature in this, but I don't think that the literature is exhaustive. You know, the problem hasn't been solved, and there could be some very interesting application areas for these kind of protocols. But we're going to move to the third protocol, and the third protocol is by far the most studied protocol in machine learning, because it's the most natural one and the easiest one to formalize and quantify and so on. And this is the one we're going to spend most of the semester playing with. Nevertheless, I wanted to introduce the other two because it's good for your thinking to realize that, you know, in some cases you can define your learning protocol and it will not be the standard one. And it's OK, and it's realistic. Let's move to protocol 3, which means some random source provides training example. Here are the examples that were provided by nature. So it's a bunch of examples, some label positive, some label negative. And now you have to come up with a learning algorithm. Before you had to come up also with a scheme for what examples to show. Now, examples are given. Just come up with a learning algorithm that will eventually learn a conjunction. Suggestions? Yeah.
You start with the ones that are true, and so, and then you start with the ones that are false. And then you start with the ones that are false, and then you start with the ones that are true, and then you start with the ones that are true, and then you start with the ones that are false, and then you start with the ones that are true, and then you start with the ones that are false, and then you start with the ones that are true, and then you start with the ones that are false, and then you start with the ones that are true, and then you start with the ones that are false, and then you start with the ones that are true, and then you start with the ones that are false, and then you start with the ones that are true, and then you start with the ones that are false, and then you start with the ones that are true, and then you start with the ones that are false, and then you start with the ones that are true, and then you start with the ones that are false, and then you start with the ones that are true, and then you start with the ones that are false, and then you start with the ones that are true, and then you start with the ones that are false, and then you start with the ones that are true, and then you start with the ones that are false, and then you start with the ones that are true,
Okay, so let's be more concrete. Start with those that are true. What does it mean? So what do I think now after I've seen this example? Yeah? I think that I need all the variables. What do I think when I see this example? Yeah?
Isn't it the case that when
Those variables. Sorry. Yeah. What do I, right, and what do I learn from this example? Okay. A lot of views here, yeah? Yeah, so I know that at least one of those that are 0 is needed. How do I represent it in my conjunction? Don't have negation in the conjunctions. I know that it's going to be a monotone one. Okay, I could make an O of the variables. You know, what I'm going to do is I'm not going to represent it. I'm going to say, you know what? Oh, what did I do here? What I'm going to do is I'm going to say, here I know that a subset of them are needed. Here I learn nothing. It's true that I do know something. I know that at least one of those 0 variables is there, but I'm not going to use it. This will give me room later on if I want to improve the algorithm to do better. Now I'm not going to use it. This I'm going to use. How will I use this? Yeah. So basically, when I see a positive example, I know that all the ones here are necessary, is a superset of the things that I need. So all the zeros I can eliminate. That's why I'm going to call this algorithm an elimination algorithm. Because it's a conjunction, because it's a monotone conjunction, I can do it. In general, no. Because it's a monotone conjunction, I can drop the zeros. This 0, in fact, I can throw it away if I believe that the data set that was given to me is consistent with a monotone conjunction. If I'm not sure about it, I have to use this positive example in order to verify that I'm okay. And again, I got a positive example, so I'm eliminating a few more. So far, x1, x2, x3, x4, x5, and x100 are on. So that's my current conjunction. I don't care about this example. It's negative. This example does not add any information that I did not have here, because it has more ones, and so on. So finally, this was my last positive example, and I got to this final hypothesis. Okay? Simple algorithm. What can you say about the number of examples? Don't know. What can you say, or can you say anything about the complexity of this protocol? Okay, let's keep this question and we'll revisit it at the end of today. But this is my final hypothesis, that's for sure, right? Is it correct? Yeah? That's the way I looked at it here. Yeah, it doesn't have to be, but I thought about it as if I'm following a sequence here. That's really what I want, right? Under the assumption that the data is consistent with a monotone conjunction, that's the only example I care about, the one that has the largest numbers of 0, because this is going to allow me to eliminate everything. But I did it sequentially here. And the reason I did sequentially is because I want to continue with this kind of learning protocol where it's an online learning protocol. I'm given an example one at a time. But let's look at this final hypothesis. Is this the right hypothesis? What's the problem with this hypothesis? Okay, so you can say many things, but the simplest thing and the most correct, the most correct syntactically, you can say x1 is there and it shouldn't be there, right? Because I showed you the truth. Now this might tell you a few things about the behavior of this hypothesis in the future, and we want to talk about it, and we'll talk about it several times this semester. But all we know now is that with the given data, that's the best we can do. No one told me that x1, no example told me that x1 isn't in the target hypothesis, so I left it there. So we just got an approximation, but it's consistent with the training data. So you can think about how good is this, what will be the performance on different kinds of examples. And you can also think about the number of examples, and as I said, we're going to come back to it. But this from the perspective of where I want to go now, it could lead us in at least two directions. One is we can continue to analyze this hypothesis with some probabilistic intuition, and this could be the probabilistic intuition that we can derive. We can say, well, this concept, this conjunction that we learn is pretty good because we never saw x1 equals 0 in positive examples. So maybe the distribution is such that x1 is never 0 in positive examples. Or maybe just appears, in a very small number with very low probability in positive example, and then we don't care. We're going to make a few mistakes in the future, but it's not going to be so bad. So overall, it's going to be pretty good. And this is really the intuition that is going to lead us to developing the probably approximately correct packed framework. And we're going to quantify this in a couple of weeks. A second direction that we can go is we can go in the direction of a mistake-driven algorithm. So we're going to ask ourselves, let's learn hypotheses and correct them only when they make mistakes. So this hypothesis maybe would be perfect from our perspective. It will never make mistakes. We made a few mistakes at the beginning when we learned until we reached this hypothesis. And from now on, we can be very happy. It's going to be good in terms of the number of mistakes one makes before you stop learning. So we can be happy with this. So these two are related but not the same direction. And we're going to start, in fact, with the second one. We're going to talk about mistake-driven algorithms, mostly because they're very simple and nevertheless very important and can tell us a lot about learning algorithms. Okay, this will lead us to talking about online algorithms, and really just to give you, again, an idea. So we're going to talk about two new learning algorithms. Both of them are going to be learning algorithms for linear functions. Perceptron with many variations. We know that will be a variation of Perceptron, but an important enough variation that we name it. And in fact, later on, we're going to look at these also from the perspective of the general gradient descent perspective. And this will allow us also to talk about a lot of important issues in learning. Importance of representation, complexity of learning, the idea of kernels, and more about the importance of features. Okay, so again, another detour, short detour for motivation is the following detour. So we talked about conjunctions. Let's assume that you don't have just 100 variables, but let's say you have, I don't know how many have there, 1 million variables, 10 to the 6 variables. But the function space is very sparse. So all the hidden conjunctions that one might care about actually have, 5 or 6 variables, right? Or you can imagine another type of sparsity where the data itself, instead of having potentially 1 million bits or 1 million features, only a small number of them are actually active in every example. Right? And we gave an example for this when I gave some NLP problem. think about this as a context-sensitive spelling correction, right? So the third word in this sentence, if you add an S to the middle, it's a legitimate sentence. Middle Eastern deserts are known. Middle Eastern deserts are known. Both sentences could be legitimate. If you think about any selection of features to express this sentence, it's going to be extremely sparse in the space of all possible features, because only those words and maybe some properties of the words that are active in the sentence are going to be active. The rest are not going to be active, but they occupy space in terms of the features, the feature space. So the question that comes up is, can we develop algorithms that depend only weakly on the dimensionality, in this case, 1,000,000, and really depend mostly on the number of relevant attributes? Notice that I'm using here relevant in two ways, and there are two different ways. One could be sparsity in the sense that how many features are really important in the target functions. This is one level of sparsity. Another type of sparsity is how many features are active in the example. It's a different type of sparsity. We're going to talk about it. But for now on, let's use sparsity without making this distinction. But really, that's a desired property if you think about it computationally, right? And of course, representation. How should we represent the hypothesis is going to be important. Okay, so we're going to start talking about it from the perspective of online learning. Online learning is really, really important. It's simple, it's intuitive, it's very natural, and you want to use it in many cases. Rather than looking at all possible data at once, you want to look at example one by one. Sometimes you have to if you have kind of a streaming data model. But often you want to do it because you know that there are 1,000,000 examples out there, but maybe you can get a pretty good hypothesis after you looked at 1,000. Why should you deal with the 1,000,000? And in fact, you think about it a little bit now when you do your problem set, because you're thinking about a batch model, the linear programming model, and you've already seen a stochastic gradient descent algorithm, which is an online learning algorithm. So you can think about this. So it's an interesting model. In terms of evaluation, we're going to ask ourselves, for example, how to quantify it, and we can quantify it as a function of, I want to make the smallest number of mistakes in the long run. Okay, so I'm going to quantify it a little bit. The formalization here is not that important. Basically, I want to say that I have a way to write down that the learner, that the model is a mistake-bound model. So I'm defining the number of mistakes an algorithm A is going to make when they learn functions from a concept class C as the maximum over all possible samples of data, over all possible functions from this concept class, because I don't know which is the target function, of the number of mistakes the algorithm A makes when it learns the function f using the sample s. It's a very standard way. I mean, nothing to make of it. Really, what I want to say that I know how to write mathematically the number of mistakes, the maximum number of mistakes that is associated with an algorithm. And then it allows me to say that an algorithm is mistake-bound if something happens. For example, I can say that the number of mistakes is polynomial in the complexity parameter. But notice that by defining it, I use the term mistake-bound. Right? So I basically say, here's an algorithm. I give it a concept class, and I tell it there is a hidden function inside this concept class. Find it. The algorithm runs, and I want to make a claim that this algorithm is going to stop making mistakes at some point. That's what it means to be a mistake, to have a mistake bound. So you could ask yourself, okay, so this is just a comment to say that it's not the most general setting. People can talk about the same kind of framework, online learning in more general terms, and you will see it in the literature, but I think most of the key ideas are going to come up in what we are talking about here. And if you're interested in this and want to go to the more general literature, it will be easier for you to digest it. So one additional comment, I don't have to analyze algorithms in terms of mistake bound, because clearly it's not the most general thing, right? You could say, I want to analyze algorithms not in terms of when they stop making mistakes, but when they almost stop making mistakes, right? So I can do some epsilon delta behavior. How many examples or mistakes this algorithm will make until it reaches a performance that I can quantify with epsilon and delta, that is, with high probability greater than 1 minus delta, it's going to make less than epsilon mistakes. Right? I could relax this, but I'm not going to do it now. I'm going to just be exact. It's going to be a worst-case model that I'm dealing with. And the reason is that, okay, the model I'm looking at is too simple. Also, when I'm dealing with mistakes, say I tell you this algorithm is going to make no more than 100 mistakes. When will it make the mistakes? Will it make them all at the beginning, which might be good, or you don't know? So given a new example, you don't know, is it going to make a mistake now or not? Because you did not reach your mistake bound yet. So it has some drawbacks. On the other hand, it has a lot of advantages. It's simple. Almost all the issues that one cares about in learning come up here. And it turns out that in a very general sense, it's equivalent to the more general models that people study, the PEC model. I'm going to talk about it probably next time. Wave my hands around this equivalence, but it can be proved rigorously. So anyhow, this is just to justify that I want to do it. But really the key question is, I'm talking about mistake bounds. Is it clear that an algorithm is going to stop making mistakes? The answer could be no, could be yes. So in fact, I'm going to make your life a little bit easier and simplify the question and ask this. Let's assume that C is a finite concept class, like the class of all conjunctions. Now your answer should be much easier. Will we stop making mistakes? Why? Prove it to me. Yeah. An even simpler argument. It again? Yes, but do I want to see all the examples? Yeah? Yeah. I meant you. Yeah. But don't confuse finite set of examples with finite set of hypotheses, right? I'm looking for a hypothesis, right? So why is it that I will find a hypothesis that is guaranteed to be mistake bound? Why is it that at some point I'll stop making mistakes? Yeah?
If your hypothesis space equals C.
Sooner or later, so what you have in mind is, if you see a function in my hypothesis space that makes a mistake, throw it out and keep on going, right? At some point, if there exists one that is consistent, you'll get there, right? So this is really the simplest algorithm you can imagine. In the ith stage of the algorithm, let's assume that Ci is the set of all concept, all function that are still consistent with the examples that I've seen. Right? So all those that were inconsistent, I threw out. Now I see a new concept. I look at the concept, and I use it to predict the next example that you show me. If it's consistent, it stays. If it's not, I'm throwing it out. So every time I look at an example, if I made a mistake, I'm making progress because I'm eliminating something, right? So, so clearly, the set of functions ci plus 1 is a subset of ci. And if I made a mistake, it's a strict subset because I eliminated the function, the one that made a mistake. So I know that it's a mistake-bound algorithm, but the number of mistakes could be pretty large, right? It's the size of the hypothesis class, right? So think again about conjunctions. You don't want to make that many mistakes. So can we do better than this? Let's think about a way to do better. The hint that I'm going to give you, what's the most important algorithm in computer science? Or the most important idea in computer science? Also, maybe there's no agreement about that. Binary search. I also think binary search is the most important idea. So can you use it here? How can you use binary search here? Right, so I want to divide up my hypothesis space in two parts. I have to think about exactly how to do it, and once I can do it in a right way, I'll eliminate every mistake, at least half of the hypothesis space. Right? That's the idea of binary search. Right? You divide something in such a way that every time you make a good move, at least half of the candidates disappear. So let's do it. So what I'm going to do is use an algorithm that is called halving. In the ith stage, let Ci again be all the concepts that are consistent with everything I've seen before. Given an example, I'm going to consider the value of the function on this example and predict by majority. What do I mean by majority? So let's consider, let's consider two sets. The sets of all functions that predict 0, and the set of all functions that predict 1 on this example. One of them is going to make a mistake, right? And I'm going to eliminate. So if I made a mistake, the majority made a mistake. Right? So if I made a mistake, I'm eliminating at least half the function. Okay? And basically, so Ci plus 1, the size of Ci plus 1 is less than half the size of Ci. And that means that I'm going to make it more, at most, log number of classes in C mistakes. Two comments. So first of all, we're going to see that this has some interesting implications. I want to say that I just used here the finiteness of the hypothesis class because it's easier for us to think. We will see next time that you can actually bound the number of mistakes magically. It really is a magic, even for infinite hypothesis classes. Right? So we will actually learn class of linear separators and argue that you can bound the number of mistakes. It's going to be a little bit more interesting argument than here. This is very simple, but there is some sort of significance to this. So let's just finish this. So of course, this is not a realistic algorithm, right? Because this algorithm really forces you to touch all the functions, or potentially touch all the functions and evaluate them. You don't want to do it. It's also not the most optimal way, because you can even be more optimal or a little bit more optimal, but it doesn't matter. the key thing here is that it does give us some upper bound, right? You can learn concepts. You can bound the number of mistakes to be logarithmic in the size of your hypothesis class. This is going to be a complexity parameter that we will carry without a long time. You know, the log of the hypothesis class. It's going to be something that is important. And it's going to be important a few weeks ahead also, not only today. But let's look at it today and see what can we say today. So let's go back to the conjunctions. OK, I gave you the truth here. So the question is, how many conjunctions? I put disjunctions here, but I actually want to say conjunctions. But it's the same thing. And also, the one that I put up there has no negations. But let's think about it in the general case. If it does have negations, how many functions are there? Class of disjunction is the same size as the class of conjunctions, right? You would agree with that. And I argue that there are 3 to the n functions, because in each place, I can either decide to put a variable, to put it negated, or not to put it. 3 options, okay? Anyone want to suggest other ways of counting it? Okay. So I have 3 to the n functions, and the log of this is just n, which means I should be able to develop an algorithm, in principle, that makes a linear number of mistakes. And if you go back to the algorithm that we gave before, you will see that this is what it does. It's not going to make more than a linear number of mistakes, right? So that's really simple. Let's think about a more interesting class of functions. The intuition, again, is this sparse example. I know that I have a million features, but I also know that the interesting functions, specifically the one I care about, has a bounded number of on variables. Only k out of the n are going to be on. Okay? This is a very realistic situation where there's a huge number of features, but only a small number of them, k, where k is really small, much smaller than n, is important. I don't know which one, but I know that just a small number are important. So how many k conjunctions are there, or k disjunctions are there? And choose k is one step, because I need to choose the k that are important. Then each one of these k could be positive or negative. So I'll have 2 to the k times n choose k. What's happening here? I wanted. So I'm using this notation here because it's easier to put on slides. So this is n choose k times n to the k. So it's order of n to the k. And that means that the log of it is k log n. So think about what it means. It means that, in principle, my bound now with the halving algorithm says that I shouldn't care so much about the million features, because the complexity here is only log of a million, which is a small number. It's 20. And I should care about k. So if I know that only 50 or something like this bits are going to be on, my complexity is going to be 50 times log a million instead of a million. Much smaller. Really much smaller. Think about growing the million to a little bit more than that. So now the question is, can we learn efficiently with this number of mistakes? Right? So I gave you a theoretical algorithm, halving, uninteresting. But at least it sets the expectation. And the question is going to be, can you develop an algorithm that does it? And the answer is going to be yes, you can. And we're going to do this next time. But it raises another question, or at least you could think about another question. What should be your target representation? So again, I'm playing the game now as if there is a hidden conjunction. Now, I can learn a conjunction, which is what we ask you to do in your problem set, or maybe we ask you about disjunctions, actually. You can learn a disjunction, but you can also learn it into a different representation, not necessarily represent it as a disjunction. And I'm going to try to motivate this, and again, I'm waving my hands a little bit, but assume that you want to learn conjunctions. Should your hypothesis space be the class of conjunctions? Is this question understood? I know that there is a hidden conjunction that I'm after. Should I try to learn a function that is represented as a conjunction? Or should I try to take maybe a bigger space? A smaller space is not uninteresting because I will not be able to express my conjunction. I'll take a bigger space that represents a lot more functions than just conjunctions and learn there. Is the question clear? It's a really important question in terms of the importance of representation in learning. And we're going to see this at least twice in the next few weeks. Here is one instance. There is a theorem that says if I have a collection of examples on n features and attributes that is consistent with the conjunction concept. So there is a conjunction hidden that is consistent with these positive and negative examples. And my goal is, I'm making my goal a little bit stricter now, so it will be more interesting. I actually want not just to learn a conjunction, I want to learn the minimal size conjunction consistent with this data. This is NP-hard. And for people that are interested, you can go back to this paper. It's by now an old paper. And read it and read a few other things that are interested kind of on the foundations of learning theory. But basically, it's what it shows, and I don't want to prove it. I mean, the intuition is really reduction from set covering. And those of you that have played these in some classes can probably do it yourself. Otherwise, it's just good to know. But the intuition is that even though I made it a little bit stricter than I want, the intuition is that perhaps, even though there exists a concept, a target concept expressed as conjunction, maybe I don't want to learn into it. Maybe because the search problem for it is going to be hard. Maybe I want to go to a larger space where each function could be expressed maybe many different ways. My search space is going to be larger, but my combinatorial problem is going to be easier. And this is what we're going to do, and we're going to do it several times. So what we are going to do is, in fact, instead of searching for things in this space, we're going to search for this in the space of linear functions. And we already said, maybe in the first or second class, that linear functions are expressive enough. For example, conjunctions are expressed there easily. So we're going to move and learn in this space. And this is one motivation, because actually it's easier to find things there. Questions? Okay, so, question?
Why do you need to estimate with a minimal number?
I don't. This is I can't prove anything interesting if I don't insist on minimal. This is the problem that we have as computer scientists.
But if it's not minimal, would it still be?
You can find a conjunctive concept, and in fact there are also approximation algorithm, because just like set covering problem, for people that know this problem, has a pretty good approximation algorithm, you can use this approximation algorithm also in the context of conjunction or disjunctions and learn an approximation algorithm. So it will be that far in a well-defined way from the minimal one. But then I will not be able to show. So I want to use it as a motivation for why representations are important. So the key issue here is that you're going to learn a concept that is consistent with the data. If you choose this representation to learn it, it could be hard. If you choose another representation to learn it, it could be easy. That's the point I'm trying to make. And it's not easy to make it, in a rigorous quantitative way without making strong assumptions. Yeah.
So beforehand, how can you know which representation?
Okay, that's of course a practical question, right? So I don't know in real life. Maybe in some situation I do, but in general you can say, who knows what's the representation of the concept? But nevertheless, you always have to choose a representation language into which you're going to learn. There's no way to avoid it. So basically the lesson here is that this selection is important, right? Because some representation language that you choose may make the learning problem harder than it should be. And you want to choose others where it's easy. That's the lesson here. Okay, yeah?
So what is the choice linear?
So in fact, we will see that this isn't the case. We will see that we can learn these kind of concepts with a linear number of examples also. And it's a much easier space to deal with. So that's what I want to start now. I want to start moving into learning linear functions. And this is just a reminder to you that we talked about it, a little bit about the expressivity. This is what we mean by a linear function. It's a function that you have a weight vector, W1 up to Wn. You have features, x1 up to xn. And we're going to say 1 if this dot product is greater than a threshold theta, 0 otherwise. And this is an expressive space, but it's not too expressive. There are some functions that we cannot express with this. Geometrically, it looks like this. It's basically the weight vector is this, and this is this geometric space of all points x, such that xw equals 0. Right? We know that. We can also move it away from the origin and get this. Okay, so what we're going to do is we're going to learn the first version of a very simple learning algorithm that is called Perceptron. It's an online mistake-driven algorithm. So I'm making here two, it has two attributes. One, it's online, which means the way I'm going to present it is you give me an example, the algorithm is going to make a prediction, the algorithm is going to get feedback. You're correct or you're incorrect. Use this feedback in order to learn something and keep on going. That's what I mean by online. It's mistake-driven in the sense that if it makes no mistakes, it's not going to learn anything. It's not going to do anything. Okay? Not all online algorithms are mistake-driven, as we'll see. In fact, the gradient descent algorithm that you've seen already, the online version of it, the stochastic gradient descent, was not mistake-driven. It always changed stuff. This is the algorithm we are doing now. It's a very, very simple algorithm because of these two characteristics. And I want to say a few things about the history. So, as I said, I would argue that it's probably the most important learning algorithm that you'll see. Even though the vanilla algorithm, it's very good, but it's not as good as other algorithms. But the more advanced version with a couple more bells and whistles actually is competitive with any other linear learning algorithm that you can come up with. It's an old algorithm, like everything in machine learning. In '59, Rosenblatt, that was computational neuroscientist, invented this algorithm. At the same time, in the late 50s, some people in Russia invented the same algorithm, and others invented variations of this. So the way he's written it, he said, from the neuroscience perspective, a target output value is provided for a single neuron with fixed input. It can incrementally change its weights on the synapses to produce the output, to mimic the output, using this perceptron learning rule. So the view that he had is this. You have this neuron, number 7 here, that you care about. You have inputs, and you have weights leading to number 7 here on the synapses. And the way the prediction is going to make is that this neuron is going to sum the weights on the active variables here, and then threshold it, and predict 1 or 0, whether it crosses the threshold or not. And he suggested a learning rule, that is a way to change the weights so that eventually the prediction here after this threshold is going to be correct, mimics the feedback that is supplied as labels, if you want, at neuron 7. One terminological thing, sometimes in the literature you will see that perceptron is synonymous to linear threshold units. I don't use it this way. Perceptron to me is an algorithm, and linear threshold units can be learned using many, many different algorithms. You will see many different learning algorithms that learn linear threshold units. Perceptron is one of them. Okay, so what does it do? So again, let's make sure that we have the terminology. So we're going to assume now that the function that we're learning is a Boolean function, plus or minus 1, and I'm going to represent it as the sign of the dot product. So if the dot product is positive, I say plus 1. If the dot product is negative, I say minus 1. I'm assuming now that x is either Boolean or could be real valued, and I mentioned, and the weight vector is real valued weight vector. And what I'm given is a collection of labeled examples, right? So x1, y1, x1, x2, xm are all examples that are n-dimensional examples. Y is either plus or minus 1. Okay, that's my input. Here is the learning algorithm. So I'm going to initialize my weight vector to 0. Cycle through all examples. You can do it randomly if you want, but let's just do it by order now. For each example, predict the label of the instance x to be y prime, which is this sign of w dot product x, and then check. If y prime is not the same as y that is supplied with the example, which means we made a mistake, update the weight vector. Otherwise, don't update. Okay? Mistake driven. How do we update? We update in the following way. We take the old weight vector and we add to it r, which r is a constant learning rate. Let's put it 1. Let's make it 1 now so it will not confuse us. So I'm basically adding y times x. Y is a scalar. It's 1 or minus 1, plus 1 or minus 1. And x is my example, right? So both w and x are n-dimensional vectors. So basically I'm taking these n-dimensional vectors and either adding an n-dimensional vector or subtracting an n-dimensional vector. Either I'm adding the example or I'm subtracting the example. And this is how I got w. Very simple algorithm. Let's see when do we do what. Right? So if I made a mistake, let's say the example was positive, and I made a mistake. I thought it's negative. So what is y? Y is plus 1, right? It's a positive example. And in this case, I'm going to add the example to w. If the example is negative, and I made a mistake, I thought it's positive, but it's negative, so y is negative 1. In this case, I'm subtracting x. Okay, so very simple. If the example is positive and I made a mistake, I'm adding x. If the example is negative and I made a mistake, I'm subtracting x. That's it. So here is Okay, let's skip this for a second. This is really what's happening, just spelling out what I just said. If y is positive, basically what I'm doing is I'm adding to w at time I the example, and I'm getting w at time I plus y. So this is my target. My previous model was this. The example was here. I'm moving it in the direction of the example. If the example is negative, I'm subtracting it from the current weight vector. So if this was the target, this was x, I'm moving it in this direction. I want to remind you of this comment that we talked about already that says it's okay for you to talk about sign of w dot product x without a threshold. And the reason, we justified it at the beginning of the semester by saying that worst case, you're going to move, you're going to add one dimension and put your theta in this n plus one dimension. And it's the same. Okay, so we have this perceptron rule. Let's see a little bit about how it works, really. So let's assume that I'm starting with my current hypothesis is this, which means the w vector is the normal to this linear separator. It looks like this. And I'm looking at this example here, and I made a mistake on it, right? So what does this mean? I made a mistake on it. Y is negative 1. I want to subtract this example from my w vector. Okay, this is w, and this is the space of all wx equals 0, right? The location, the geometric location of all x's such that w dot product x is 0. Right, this is this line. And this is what's going to happen, right? So I'm going to take my x. This is my x. I'm placing it here on w. And now I got this, right? So this vector, which is here. Is this w? I have to choose a space. Where are the positive and where are the negative, right? I decided that if wx is positive, then I call it positive examples, and the other side I call it negative examples. Yeah, I could have chosen otherwise, but it seems natural to. Okay, so then you can continue, look at, now I have this as my w, and I see another example. Again, it's negative. This is the example, the red vector here. I'm placing it on the head of my w, and my next example is going to, my next w is going to be here. Very simple algorithm. Okay, so a few comments that are important on this algorithm. So this is the algorithm again. Everything is clear? Really very simple algorithm. You can imagine that it's also trivial to implement this algorithm. One comment, notice that if x is Boolean, I said that, I don't care what x is. Could be real valued n-dimensional vector, could be Boolean n-dimensional vector. But it's important to realize that if x is Boolean, notice that only the weights of the active features, those that are on, are going to change. Right? So you can look at it here. What's happening here? Okay. My weight vector, this is my original weight vector here. And now this is going to be my new one after I added x. But notice that if x2 here was 0, I don't need to touch w2. Right? So really, I can write the algorithm as look at all the active features and update the weights of the active features. Why is this important? Yeah? So again, dealing with sparsity is really crucial. We talked about the case, the realistic case, where I have 1 million features, but only 50 of them are on. All I need to do is to keep track of those that are on and just update 50 weights, rather than check 1 million weights, right? So you want to implement your algorithms this way, so it takes this into account. The other comment that I wanted to make, and again, it's with an eye to the future, is that you can think about the condition w.product x greater than 0 this way. Right? This is a logistics function that some of you have seen. 1 over 1 plus e to the minus wx. And I want to ask whether it's greater than a half or less than a half. And it's very easy for you to see that, you know, if wx is 0, then I get here 1 plus 1 over 1 plus 1. It's exactly a half. If, on the other hand, wx is positive, then I get e to the minus positive. So you can look here at the graph, and you will see that in this case, I'm going to get the denominator is less than 2. So I'm going to be greater than a half, and so on. And this is going to be important because it will have a probabilistic interpretation. Yeah?
So this is essentially going to reduce down.
It will be equivalent in some cases to a logistic regression. Yeah. And that's really the point that I'm making here. But we're going to talk about it in more details later. This is just kind of planting a seed. And you can see that you can write a logistic function that behaves exactly the same. Okay. Yeah. Yes, it could be. Very good point. So far, I said nothing, right? I just gave an algorithm. And it's true that, you know, I'm moving the line around. And I'm hoping that at some point the line will stay in a place that all the positive examples are on one side and all the negative on another. But I could certainly make a mistake in the other direction. So the two questions that you want to ask is, I'm going to skip it now. I'm going to go to this because this is going to start us, prepare us for next time. The question is, will it converge? And the answer is, and it's a really beautiful thing that we're going to start with next time, that yes, if the data is linearly separable, that means if there exists a linear separator that leaves all positive on one side and all negative on the other, this algorithm is going to find it. And in fact, it's going to find it quite quickly. On the other hand, if there isn't, it will not find it. And it will keep trying. So we'll have to ask the question of, what can we do so it will stop at some point that makes sense. But the key thing is this part. It will find it, and we're going to ask the question how long it will take it to find it, and we'll see that it's actually pretty nice. And we're going to use this mistake-bound idea that we talked about today in order to show that actually Perceptron, in a well-defined sense, is a mistake-bound algorithm. Final questions? Yeah? The theorem that we'll prove at the beginning of next time will show that it doesn't matter. Now, in practice, of course it will matter, right? Because it will converge faster under some order than under other orders. But the theorem is not going to take the order into account. Okay, let's finish here. Have a good weekend. People that want me to sign on the form, please come forward now.